All right, here we go. So, if you remember, today we left off on number 13 in the notes, and that's where we'll pick up today. Welcome to Mr. Debley's classroom. Miss Hayner was working on something, so my apologies for the new venue. Organic chemist, but we do have a whiteboard, so I think we'll be all right. So, if you remember what we're leaving off with today in class was that there are three types of organic reactions. The three types all involve bonds. We have substitution, addition, and elimination. Addition, something like that, and elimination. And in terms of what we're talking about here, we're talking about atoms added to the organic molecule. So with the substitution, there is no change in the number of atoms. And as a result, the number of sigma and the number of pi stay the same. With addition, we are reducing the number of pi's because we're adding more atoms to it. And we are increasing then subsequently the number of sigma bonds. And then lastly, with elimination, we'd be doing the opposite. If addition is adding, obviously with mathematics, elimination is removing. And so elimination would be increasing the number of pi bonds because you are taking things away from the organic molecule. And if I take things off of a carbon chain to stabilize, I must do so with a pi bond. So I'm going to increase the number of pi's here, and I'm going to decrease the number of sigma bonds. Now that's what we left off with today, and I gave you a few examples in class. But what I want to do today is I want to finish up that section of notes, and I want to talk a little bit in detail about addition reactions specifically. So if you look at number 13 in your notes, it says addition is a reaction which elements are added to a starting material. In other words, atoms are added to our organic compound. Atoms are added to the molecule. A, addition reactions involve pi bond that is broken and sigma bonds that are subsequently formed. In other words, an addition reaction is generally going to involve an alkene and alkyne as the starting reactant and an alkene or alkane being the product based on what we start with. B, addition reactions are an important method for introducing new functional groups. In other words, an organic chemist gets pretty excited when they have the opportunity for an addition reaction because that means that they had at one point a pi bond. And a pi bond can be universally turned into kind of anything. C, when a reagent is water, it's stated that an alkene will undergo, are you ready for this? If we're adding water, same thing would happen to us. We would call that hydration. Here they also call that a hydration reaction. Bill and Ted got together in the back and they said, let's call it literally what it is. And bada bing, bada boom. Adding water, hydration. Hydration reactions usually occur with a strong acid and water being added to an alkene and heated above 100 degrees Celsius. So we need a strong acid such as HCl or H2SO4. H2SO4 is a great acid to use because it's big and bulky and clunky and kind of leaves the reaction alone. But below I've got an example here. So let's use ethene. Ethene, eth, two carbons, ene, double bond. So we have an ethene. One of these bonds remembers a sigma, and one of these bonds would be a pi. Sigma, pi. And then we're going to add to it aqueous, there's my HOH, and we're going to use an acid like H2SO4 to speed it up. Now what's going to happen here is I'm going to add water to the molecule. One side of the pi bond being broke would result in a hydroxide. The other side of the pi bond being broke would be the hydrogen. So this is a hydration reaction that is also an addition reaction. D, when the reagent is a halogen molecule. So instead of me using HOH and H2SO4, what if I start with ethene this time and react it with bromine, Br2? Well, now I've got bromine, and bromine is a high electronegative element, just like hydroxide in the previous. And if I've got a pi bond, I have two weakly unbonded electrons that are sort of just talking to the other molecule. And as such, bromine would come in and interact, and I would produce a di-substituted alkyl halide. Now notice here we added a halogen. So what did Bill and Ted decide we should call this? They said, you know what? We're adding a halogen. Why not call it halogenation? D, when a reagent is a halogen molecule, a di-substituted, di means two substitutes. put on it. A disubstituted alkyl halide is produced. These usually do not require a catalyst because bromine and all of the halogens are highly electronegative. They love the electron-rich region of a double bond, and they love that they can grab kind of unbonded, loosely bonded electrons that are involved in the unhybridized p orbitals of those carbons. They do not require, because of electronegativity, an example of it would be this. Now, this is an interesting test. We talked a little bit about testing for a reaction going to completion today and the previous day about testing for pH change. Well, this one's interesting because I start with a clear alkene and I react it with a red substance, bromine, which is a halogen. It's a liquid and it's red. But what's really interesting is when I get back to this disubstituted configuration, I'm taking clear plus red, and you might think that make me pink or a light rust or something like that. Instead, what it does is it goes back to being clear. So this is a great way to test to see if you have any pi bonds, because if I keep adding bromine and the bromine keeps going clear, but then all of a sudden I add one more drop of bromine and it stays red, I will know that I have broken all of my pi bonds and I now only have sigma bonds present. So that's another test for you to put in your tool kit. If we look at this, it's ethene plus bromine producing 1,2-dibromoethane. A question that you may want to answer in your head or should answer, why wouldn't they both go on one of the carbons? Remember, whenever I ask a why question, always answer with a foundational rule, and I believe you can come to that conclusion. E, because of this, bromine, which is red, can be used to test a solution to see if it's saturated. Saturated would mean every molecule is holding everything it can. If it's holding everything it can, we're talking about sigma bonds, not pi bonds. F, when the reagent is a strong acid like HCl, HBr, HI, HF, a monosubstituted alkyl halide is produced. So why would this change result in a monosubstituted alkyl halide? Well, if I have 1 molar ethene and I have 1 molar hydrochloric acid, I would have 1 pi bond for every HCl combo. And what would result in that? A monosubstituted alkyl halide. There's the proton, the hydrogen, and there's the chlorine, the halogen. And this would produce chloroethane. But I have a question for you. What would happen if I would double the concentration of the acid relative to the alkene? Well, if I doubled the concentration, wouldn't I have twice as many high electronegative elements like chlorine to interact with this loosely held pi bond configuration? And if that were the case, couldn't I then get something similar to what I had when I reacted with a halogen and use twice the molarity? Now I get a disubstituted alkyl halide. So there's 2 ways to make those. When the reagent is a strong acid, and F is where we're at, a monosubstituted alkyl halide is produced. Because halogens are involved, catalysts are generally not needed here because of the increased electronegativity of the chlorine, the bromine, the iodine, the fluorine, etc. So if you look in your notes, you have ethene plus hydrochloric acid would yield chloroethane, unless I have twice the concentration of the acid, then I would produce 1,2-dichloroethane. G, the addition of a halogen to an alkene to produce an alkane is referred to as hydrohalogenation. The addition of hydrogen to an alkene to produce an alkane is referred to as, I said that all wrong. In the addition of hydrogen, just hydrogen. So Bill and Ted got in the back room. They said, okay, we're just adding hydrogen. I wonder what we should call this. Well, we're kind of generating something with a lot of hydrogens. And they said, you know what I think we should call it? We should call it hydrogenation, 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 hydrogenation. So if you've heard of hydrogenated oils, what are those? Those are lipids, and we'll learn about those in our last unit this semester. But they're lipids that have been hydrated, or not hydrated, hydrogenated. Hydrogens have been added. So they've been saturated with hydrogens. Hydrogenation does require a catalyst. Why would hydrogenation require a catalyst? Pause the video, maybe answer it. Hydrogenation would require a catalyst because we're changing something important here. When I'm hydrogenating it, adding hydrogen, I've lost that highly electronegative element that I had in the halogens that I had in my simple strong acids like HCl, or that I had in chlorine, or I had in bromine, etc. Now I have something that's pretty electronegative, but not relative to carbon. And so as such, I'm going to need a catalyst to speed this up because I ain't got all day. Catalysts, remember, speed up reactions, but they're not involved. They're going to efficiently help transfer electrons. Well, if we're going to help transfer electrons efficiently, wouldn't we want a metal? Just like when we run electricity through a wire, it quickly transfers electrons from point A to point B. Same thought here. So I would want to use a metal such as platinum, palladium, Pd, or nickel. Let's be fancy here. Oh no, the lights shut off. Gosh darn it. There we go. Man, life on the frontier is hard. And let's use platinum so we're balling big time here, students. So I've got platinum to allow for the electrons to transfer more quickly, and I'm going to reduce this from an alkene to an alkane. And this is hydrogenation, just adding hydrogen, hydrogenation. And 14, addition and elimination reactions are complete opposites. Ideally, you've picked up on that. By that, I mean addition reactions make 2 sigmas and break 1 pi. Eliminations make 1 pi and break 2 sigmas. I hope this helped clear up a little bit on addition reactions, as well as review briefly addition, substitution, and elimination reactions. Students, this is video 1. There is a video 2 over oxidation and reduction. Thank you for watching these. I miss you. Bye.